Okay, so we are extremely grateful to have Marta Mazzocco as our colloquium speaker for this second edition of Junior Global Poisson workshop, and she's going to give a lecture on quantization.
Thank you very much, and I am grateful to you instead for giving me the opportunity to look like a fool for an hour. So I'm going to discuss some really basic ideas about quantization. My point is that I'd like to reach as many as possible in this audience, so I will neglect all the people who know about this stuff. They will learn nothing. You can go and play Tetris on the computer. So I would like to start with a question, which is the following. Whether real numbers are actually innately commutative. So and to answer this question, I would like to give you an example. And I'm thinking about, I'm thinking about when I retire, what do? I could open a restaurant. So this restaurant ideally will have a certain number of tables. And I will be able maybe to cook for a certain number of customers. And then to get organized, I will need to introduce an operation, which I call x times y or times or y, whatever. And this by definition will encode how many people are coming into the restaurant. So of course, this will be if x denotes the number of tables that are occupied, and y denotes the number of people on each table. Then, of course, the total number of customers that I will have in my restaurant will be x times y. But then I might think about how many other tables I've left, and I want to retain this information, right? So, because if I receive some phone calls, even though maybe I can cater for all those people, I might have many tables occupied and I might not be able to book for further tables, okay? So I will have a certain number of people, and then I add a term with some coefficient, and this is telling me how many tables are left in the restaurant to be occupied. And also I might want to add the information about how many menus I can cook. So I will do that by saying that we have a term which is C minus the total number of customers, sorry. Okay. Right. Okay, so this number is going now to tell me a little bit more information than the usual product of two numbers, because it retains some information about how many tables I've left. In fact, the second information is redundant in a sense, so we can also forget it. But the first order in H bar, this is quite important information as well as the total number of customers. So if I do instead y cross x, well, this means that I have y tables occupied with x people on each of them. So the total number of customers is the same, but the total number of tables left is different. Okay? And so we see that with this operation, we have that x cross y minus y cross x gives me 0 at order h bar to the 0, but at order h bar gives me x minus y. Okay? So we have that this operation is not commutative anymore. And so my answer is that no, real numbers are not innately commutative, because in fact we can always think of the product of two numbers telling us the number of objects in how many groups. So when we say to children, if I have 5 apples in 3 baskets, how many apples I have? Well, I have 15, but they are divided in groups of 5 in each basket. Okay, so let me move on to maybe a little bit of a more. So this is kind of my way to justify the fact that I do research in quantum stuff, so that it's useful. You see, if you want to open a restaurant, you must know your non-commutative algebra. Okay, so I would like to give you another example, which is perhaps a little bit more instructive. And this is the quantization of the algebra of functions on the group SL2C. Okay, so we think about the group SL2C in representation. Oh, sorry, it's getting really dark here suddenly. Let me open, switch on the light. So we think about representing this group on a two-dimensional vector space. So this may be the group of matrices A, B, C, D, such that AD minus BC is equal to 1. And so we can think about the space of the algebra of regular functions as the set of polynomials, in the variables A, B, C, D, modulo the ring of polynomials modulo the ideal generated by this relation. Okay. And now I would like to quantize this object. Okay, so the main point is that before I quantize, we have that, for example, AB times BA is the same. We are thinking about this C being numbers. Okay, this A, B, C, D are numbers. And now I would like to quantize, which means I would like to deform this commutation relation into something which is no longer commutative, but such that maybe we recover the original relations in a certain limit. So going back to the restaurant table, example, we see that this product is not commutative, but when H bar goes to 0, then it becomes commutative. And that's the same thing we want to do here. We want to quantize the A, B, C, D to some objects, which I denote by some symbol A, B, C, D, which are no longer commutative, but which satisfy some relations between themselves. And these relations will eventually give me back the relation we had in the classical case. So the basic idea is that I would expect that this object will quantize to some free algebra generated by these elements, free associative algebra generated by the elements A hat, B hat, C hat, D hat, up to some idea, which now I will try to guess. Okay. So at the moment I'm doing just guesswork. I want to show you, or at least convince you, that a lot of quantization is actually very intuitive. Maybe I'm lying a little bit, and we'll see later in what way I'm lying. So the main information here is that we have an ideal, and ideally, I would like to quantize this ideal. And let's look at this. So I think it's quite important that we highlight this guy. So in some way, we would like to think that whatever we get as quantization of this relation, it will somehow be preserved and it will be an invariant in our algebra. The quantization or quantum determinant will be invariant. So let's start guessing a little bit just before so one way we can do this is by saying, okay, I need to tell you what is A times B in terms of B times A, okay? And so many, you know, the first easiest possible case is that you say, okay, A times B is not quite B times A, but is B times A multiplied by some quantity Q, and this quantity Q, when this quantity Q goes to 1, then A will go to A and B hat will go to B, so that we recover the classical object, okay? So, okay, then we say, okay, let's see how AC will go, and I'm using kind of this expression, so we see that in the determinant we have a part which is AD and a part which is BC. So somehow we put A and D together and B and C together. So because I've decided that A and B satisfy a certain relation, I'm going to say that the same thing is valid for C. And then, okay, I will see, okay, let's do also D. And I will say that, oh, sorry. For D, I will go the other way around. BD is equal to Q DB, BD, okay, CD, okay, Q CD. Okay, so far so good. If we do this, we immediately see that you can exercise here. You can show that then if you take AD and you do the commutator with BC, they commute, okay? It's very simple. You just use the relations that I wrote there. So now we could keep going. You see, so far I've just given you the relations between A, B, and C, or D, B, and C. We didn't look at how A and D do, or B and C do. And the point is that I'm trying to make is that we have no freedom left, essentially. We have very little freedom left. So, for example, suppose that we want, I don't know, that AD is equal, commutes with that A and D commute. Well, this is going to create a problem. Essentially, what you can prove is that because you would like whatever is the quantum analog of the determinant to be, you want it to be still there. We want this relation to be preserved. If we impose such commutation, we will get that the algebra disappears. So we will get that B and C are 0, for example. Let me show you. So, for example, assume, okay, so I want to replace the relation on the determinant by the quantum relation. Let me write it in red. So I will have A, D, minus, maybe we can put some coefficient in front. Let's me call it f of q, some coefficient in front of B, C, and we want this to be equal to 1, okay? So this will be our quantum object, which replaces the quantum determinant. At the moment, I'm not even choosing what is this f. And now let's see what happens if I decide that A and D commute. Well, if A and D commute, we have that we have that dA is actually can be written as d AD d minus 1, okay? And now I use the determinant to express AD. So I have d 1 plus f of q bc d minus 1. And now I'm going to simplify this. So d times 1 times d minus 1 is again 1. F of q is some function of the parameter which I assume to be commutative with everything. So I can rewrite this as dbc d minus 1. And then I can use my commutation relations. For example, I can commute these two. And this is the relation here. Okay, so I know that dB is 1 over Q BD. Okay, so normally I get incredibly lost when I'm doing this sort of computation. So B, D, C, D minus 1. And now I want to use this relation here. This the second one here. So this is DC is oh, I wrote it wrong there. Oops, not this one. Okay. So DC is equal to 1 over Q CD. So that I get, finally, I get 1 plus F of Q over Q squared. Right? B, C. And this is not, so, okay. So let's go back to what we wanted to do. We wanted to say that AD is equal to DA. So if that was true, let me do it in another color. If this was equal to AD, then, but AD is actually equal to 1 plus F of Q BC, what we get is by comparing left-hand side to right-hand side, so comparing this side to this side, is that then the only way that can happen is either F of Q is 0, which we don't want, or BC is 0. Okay? And that's not good, because then we are putting to 0 some generators, which decreases the dimension of the quantum object with respect to the real, to the classical object, and therefore that is not allowed. So what we find is that, of course, we cannot impose this relation, but what we can do is to impose. We can do something slightly different. So I will now remove the blue part, okay, or maybe I can just remove it this way. So this we don't want, okay. The part in which I computed D times A is exactly the same, but now I'm going to use, so I want to write what is dA minus AD. So for dA, I'm going to use what I've just proven. So it's equal to 1 plus F of Q squared BC. And AD, I'm going to use the determinant, which is minus 1 plus F of Q BC. So we have that the commutation relation between D and A is given by some, whatever F of Q is, 1 over Q squared plus 1, minus 1, sorry, minus 1, B, C. Okay? So whatever you choose for this f of q, for example, it could be q. Normally people like to use q, because then this, if f of q is equal to q, then this becomes much simpler. Looks nicer that way, okay? But what I wanted to show you is this typical thing of quantizing systems, is that whenever you have a relation in your classical algebra, then then this relation will interact with the way you can quantize in a non-trivial way. Because if you don't do, if you're not careful to take into account the relation, you will end up with an algebra at quantum level which has a dimension lower, at least one dimension lower than the one you started from. Let me check because I see that I have some questions in the chat. Yeah. Okay, cool. So this was kind of a little example exercise, if you like, that I've taken from a book, old lecture by Fadiev and Takhtajan. It's very nice, I think, because you can actually play with your hands if you've never quantized before. Of course, there is a formal way to do it, okay, formally.
Sorry, one question.
Sure.
How did you get 1 over q squared minus 1? Isn't it plus 1?
I had this minus here. So this part comes from dA, and then I'm removing minus AD. Is that where you were asking?
Yes, so it is AD is 1 plus, so maybe in the previous line.
There should be, where you crossed out minus. No, I think in the second last line.
Yes, there is a minus here, sorry.
Yes, exactly.
Sorry, let me put it in red so that you see where I've made my correction. Yeah, cool.
Okay, yes.
Thank you. See, never do these computations live. That's my second take-home message. Okay, so let's do it formally. Formally, what do? We take a representation of SL2 in C2, so let's choose vector representation on C2, and then we know that SL2 acts by multiplication, matrix multiplication. Okay, X, Y, so this guy belongs to D. And we can also, you can use this to define an algebra homomorphism between C, X, Y, the algebra of polynomials in two variables, and and the same, and the space of functions on SL2 C cross C, X, Y. So what I'm doing here, this guy is just simply the symmetric algebra. On V star, which is identified with V. And so it's the algebra of polynomials in V. And what we do, we fix a T. For every fixed T, we associate to a vector X, Y, to X and Y. I mean, let me write it this way. X, Y will go to some symbol which we call A tensor X plus B tensor Y. So it's a tensorial way of thinking about matrix multiplication, if you like, plus D tensor Y. Okay? And then what we do when we quantize, the idea is that we want to deform this guy, but we deform it also. So the deformation, essentially, the deformation of the space of functions is dictated by the deformation of the space of polynomials of two variables. So we deform, first of all, we deform the space of polynomials in two variables into simply something like this. Okay, this means that x times y is exactly what I was doing before, qyx. And now what we do is that we use this map and we insist that this is still an algebra homomorphism, which means that we want that if I call this will be my quantum mu x and the other one will be my quantum mu y, what I'm imposing is that A cross x plus B y x c x plus d y is equal, so this essentially, this part is, this part will be equal to q yx, so c cross x plus d cross y times, sorry, times the last bit, a x plus b y. And exercise for you is to prove that if we impose this property, we obtain exactly the same quantum relations that I derived previously just by using common sense and intuition. So this was this idea. This was the idea that we got before, so it was generated by these relations. Let me copy them. And also the extra relation, which we had with a d. Oops. Okay. All right. So that was the more mathematical, if you like, algebraic way to do it, is the idea that you do a deformation of the algebra of polynomials and that this deformation carries through as carrying through the algebra homomorphism between the symmetric algebra and the symmetric algebra times the algebra of functions. Okay. Are there any questions on this part? No. Okay. So I would like to do another thing, which is I want to consider. I realize that I already spent half an hour for these two really introductory examples, so I'm going to be a little bit. Let me think how I'm going to do this. Right. Okay, so let's okay. So in this lecture, I'm going to try and quantize a specific Hamiltonian system that I like very much. So I will use some of these ideas to quantize a system of equations which are called Schlesinger equations. I'm not going to explain to you where they arise, why we care, or anything. I will just give the equations to you, and then we will kind of reach some interesting quantization, which was actually produced by Reshetikhin in the early 80s. And the reason I'm choosing this example is that, in fact, we are working in collaboration with Ilya and also with Volodya Rubtsov to carry out this quantization for many more examples of these Schlesinger equations, or namely cases of the Schlesinger equations where we are very close to higher order poles, but that's only for experts. So let me, so there is nothing new in what I'm going to tell you in this lecture. It's a lecture, it's not a seminar, so there is no new result yet for today, but at least I can tell you about how we understand this, this result by Collier-Reshetiki. Okay, so I'm going to consider a Hamiltonian system on, well, let me start first of all to consider a Lie group. Well, actually, in fact, let me take again SL2C because it's just as good as any other, and actually it's very pretty. I denote by G, it's the algebra, and by G star, the dual algebra. Okay, and the space of functions on the dual, he is endowed with a beautiful structure of Poisson structure, which is called the Lie-Poisson bracket. And this is constructed in the following way. It's essentially, you identify the dual of the dual with the Lie algebra, and then given any functions f and h inside, so functions of on the cojoint, on the, yes, on the G star algebra, you define the Poisson bracket between f and h, applied to an element, this is in G star. By definition, we take it as trace. Well, okay, I'm already thinking in representation theory, but we can take a killing form to identify G and G star, and we can take the evaluation of psi on the commutator of the differential of f, oops, and the differential of G, H. So the idea is that here, so this guy belongs as before to G star. These two guys, they are differentials of linear of functions on G star, so they belong to G star star, but because we have made this identification, we can think of them as elements in the Lie algebra. Okay. So let me just show you in the example of SL2 how we compute these brackets. So in the algebra SL2, we can take the basis of elements in this form. This is normally called E, this is normally called F, 0, 1, 0, 0, and H, which I call E3. There is a reason why I want to be able to use summation indices, 1, 0, 0, minus 1, okay? And the commutations relation, so the Lie bracket on the Lie algebra is given by these commutations relations. I like this example because you can just compute it by hand. If you are tired in the evening, instead of doing Sudoku, you do this one. Okay, and so we can write the commutation relation with shorthand notation, in which I denote the coefficients with upper index and lower two indices, so that this notation means that we are summing on gamma. Okay, Einstein convention. So then we can compute the bracket, the Poisson bracket. What we are going to do, first of all, this is in the Lie algebra G. So I need, first of all, oops, that should be a G. I need to to take the dual, and on the dual we can select a dual basis. So the dual is again SL2 in this case, but we want to take the dual basis in such a way that it's orthonormal actually to the given basis. So I will denote by E1 star is going to be the matrix, matrix wise is going to be E2. E2 star is matrix wise E1, and E3 star is going to be 1/2 E3. Okay, this is because I want that if we compute the killing form, so trace of E alpha star E beta, this is the Kronecker delta. So that's why we have this this strange notation, but it's very helpful now, because what we are going to see now is that we can define a function f alpha by taking the trace. So for every psi, or let me call it A, for every A in G star, we can take the function of A to be the trace of A E alpha. Okay, so this is essentially the killing form A E alpha, and then what we find is that when we compute the differential of this function, this differential is actually E alpha itself, and so the Poisson bracket on these functions. So if I define f alpha, f beta, then the Poisson bracket between them is simply satisfies the same formula essentially as f gamma. Okay, so what we see is that the function, the space of functions on the dual of the Lie algebra admits a Poisson structure, and this Poisson structure is such that the map from SL2 with the standard Lie bracket to the space of functions on G star with this Poisson bracket is an algebra isomorphism. Okay, so let me just write this little theorem. SL2 with the standard Lie bracket is isomorphic to the space of functions on SL2 star with the Poisson bracket, which is called Lie Poisson bracket. Okay, so why all this tiring thing is because now I want to consider a special Hamiltonian system on many copies of SL2, and then I'm going to use these ideas to quantize it. So I'm going to take a Hamiltonian system. Oh, let me now, I need to show you my side. Oops, no, sorry, made a mistake. Okay, and now this way I want to show you. Okay, so it did work yesterday, I promise you. Okay, right. So what I'm going to do is to keep this very small on the left, but at least you see I put there my matrices E, the commutation relation, and the Poisson bracket. Okay, so that we have it there and I don't need to jump up and down in my notes. Or maybe I'll jump anyway, but at least the intention was good. Okay, so I'm going to consider a specific Hamiltonian system. Just a minute. It doesn't allow me to write anymore. Hello, please allow me. Oh. On SL2 star, many copies. Oh, I can take direct sum, I really don't care. Okay, so this system, we think about AI. being an element in the Lie algebra SL2, start in the dual of the Lie algebra, and we take the Hamiltonian Hj to be the sum from 1 to n, I different from j, of the trace of ai aj, uj minus ui. So let me tell you what everything is. We have n copies of SL2, and we think about them n elements. So we will take a n pole of matrices in there, okay? And then we have n Hamiltonians in the times u1, un, so that the equations of motion of this system are dAi over duj will be the Poisson bracket of ai with hj. And this Poisson bracket, what is it? Is exactly what we had before on each SL2. What does it mean? Is that if I have two functions, one is a function of the entries of this matrix, and one is the function of the entries of another matrix, they will Poisson commute because we think of them as lying in different copies of SL2, and we think about these different copies of SL2 as commuting between themselves. But if we take two functions of the same matrix, then we are within SL2, the same copy of SL2, and in there we use the Poisson bracket that I gave you before, okay? Right, okay, so I want to quantize this guy. And what do I do? Well, it's, in fact, let's quantize first. I want to quantize 1A. Okay, so what I'm going to do is to really think about the dual of the Lie algebra like a vector space. So what it means that my A, we can write it as a linear combination of elements in the basis, in the dual basis. And in fact, this will be a linear combination of sum over alpha of E alpha A times E star. So what I'm saying here, this is the trace of E alpha A. So what I'm saying is that let's remember what our dual basis is, yes? So the dual basis is written, I don't know why it doesn't allow me. Oh, here it is. And now, so we think about that, okay? And so what I'm really saying is that we think about, if I have, for example, a matrix, I'm sorry to do this, it's a bit stupid, but I will need it later. What does it mean? It means we have A11 times, oh, I forgot a half here. Times 2A11. Oh. Okay, so hopefully this is correct. Okay, that's all what I'm doing. Okay, and this guy is just E3A. Okay, nothing really complicated. I'm just expressing everything in a form that we can handle. Okay, and then so I can think about the components. What I'm trying to say by excavating myself in this hole is that we can think about the components of our Hamiltonian, or of our matrix A as functions over SL2C, okay? And these functions are simply very natural functions of this type. That's all what I'm trying to say. So now I want to quantize. What does it mean?
Could you say what are the parameters uj?
Excuse me?
What are the parameters u?
Oh, those times, many times. So I'm considering a Hamiltonian system with many times, okay? You could also decide that we just consider one time, and then we have only one Hamiltonian, and I will quantize that one Hamiltonian, okay? But in fact, it's more interesting when we have many times, because we will see that the quantization actually leads to an equation which is known in the literature and is called the Thermological Equation. But if you find it difficult to think about a system with many times, just think about fixing. You could fix, okay, we could fix U0, U1 to be 0, U2 to be 1, U3 to be 1 time, and all the other don't exist, so n equal to 3, and only one Hamiltonian, so we only have H3, okay? There are reasons why I consider this system, but they're not part of this lecture. Okay. Okay, quantization means that we want to go from functions to operators, okay? Let's actually, this was the space of function, not very good F. Let me use a different F. Okay, so, and the idea is that we still want to do some sort of deformation quantization, so the Poisson bracket between two functions will go to some commutator between two operators. So what we do, we use precisely this idea, and what this corresponds to is that we are thinking about A to be a function which has components 1/2 F3, F2, F1 minus 1/2 F3. I remind you, these functions Fi are these guys. So it's written there too, in this. Okay, F alpha of A is equal to the Killing form applied to A and E alpha. So when we quantize, we want to go to some quantum object, which will be some quantum matrix in which the entries are quantum objects. And what we are going to do is to replace each of these guys with an operator. But we want to use the fact that we are in SL2. And let me remind you that you see, we sort of have something for free. So what I'm trying to say is that the entries of the matrix A satisfy some Poisson brackets due to this relation that we derived at the beginning. We want to quantize it, we want to transform this Poisson bracket in commutation relations, but we already have a recipe to do that, because we know these relations. Those define a beautiful commutation relation which defines a Lie algebra. So the most natural thing in the world, if you don't know even how to read and write, is to simply say that when you quantize, you substitute in this way. So automatically, I'm having some object in which the entries are operators, because now they are matrices, which by definition and construction is satisfying that relation, namely the Poisson bracket between two elements is mapped exactly to the image of that Poisson bracket, okay? Because of the algebra homomorphism between SL2 and the algebra of functions on G star. Okay, so let me write this guy in a better form. So A star, we can, and this is little exercise of tensor products, you can immediately verify that actually this is equal to the tensor product, the sum of the tensor products of E alpha star cross E alpha. Really, just exercise. You can do that. Now, this guy is called R matrix. So this is the famous Semenoff-Tian-Shansky R matrix, and it appears really, really naturally when you're doing SL2 quantization. So now let's go back to my Hamiltonian. So the Hamilton, oh, I have it there. I have it on the left. It's the first time I try to do a seminar with this left thingy. I'm really pleased. So let's quantize that guy. And so you see, for now, I've quantized one matrix. So one matrix means that I had my A. So let me perhaps say, I had my A, it was an element of G star. And then to this A, I associated an operator A, and this is an element of G star cross G. Okay? And now if I have many elements, E1, AN, they belong to, well, the direct sum of all these G's. I associate to them something which is in G star cross G cross G. So what I'm trying to say is that I will quantize A1 to the sum over alpha of E alpha star E alpha cross identity and minus 1 times. Then I will do A2. A2 will go to sum of over alpha of E alpha star cross identity cross E alpha cross identity, and so on. Okay, AJ is going to go to sum over E alpha cross identity. At J position will have E alpha, and then the rest is identity. All right. So now I want to quantize the Hamiltonian. So we need to take the product of matrices A and compute the trace. I'm sorry, I will actually, I think, be on time, just. And so now, for example, suppose we want to take A1, A2. Well, then we use the rules of tensor products. So we'll have a double sum now. We will have E alpha star E beta star cross E alpha cross E beta cross 1 to 1. Oops, sorry. Okay. And okay, so there is a little bit of a thing here that you might not be happy. I'm identifying G and G star here, and this is an element in the universal enveloping algebra if you want, but I'm dealing with matrices, so we know how to multiply them. It's not a big deal. And then I want to take the trace. So the trace acts on the part which is coming, not the quantum part, it acts on the classical part, the part that is coming from the classical side. And so when I do the trace, you can compute the trace of E3 star E3 is equal to 1/2. The trace of E1 star E2 star is 1, and all the others are 0. So what we get, if we carry out this computation, we get that this is equal to sum over alpha only of E alpha star cross E alpha cross identity. So what we find is again the R matrix of before cross identity, identity. Okay, and if I was to do, if I were to do trace of A, I, A, J, what I would find is the sum over alpha, and then I would get E alpha. Have I done a small mistake? Sorry, I've done a small mistake. No, I haven't done a small mistake. I skipped the passage. Maybe I should do this passage, because otherwise, if it confuses me, I cannot imagine what it's doing to you. Let me perhaps be a little bit more painful here. So let's look at this. When I do the trace, this part will be substituted by a number, and then I will have a tensor product of elements in the Lie algebra. Because many of these traces are 0, and the only one which survive are these ones, and due to the game we have between dual bases and non-dual bases, what happens is that I'm substituting, I'm identifying, essentially, I'm identifying this guy with, well, yeah. Yeah, it's okay. Let me do it. I'll just do it. I will say, okay. So for example, say we have alpha equal to 1 and beta equal to 2. Okay. So for alpha and beta, alpha equal to 1 and beta equal to 2, we have 1 cross E1 cross E2 cross all the rest. No, but E1 is the same as E2 star. So I will get E, so this was not, yeah, sorry, that was not a tensor product, it was 1, just simply 1 times. And then it will give me E2 star cross E2, okay? That is the step that I skipped. And so the first one comes from this identification, and it's in the position 1. The second one is in the position 2. So when I do the trace of AI, AJ, what I will find will be the sum over alpha of identity cross, at certain point I will have an E alpha, I will have some more identities, and then at a certain point I will have E alpha, and some more identities. This will be in position I, and this will be in position J. And this is what many people denote by Rij. So the original R matrix we had was R12, because we put the first tensor product in the first space, the second tensor product in the second space. Rij means that you have identities everywhere except in the ith space and in the jth space. Okay, so why am I insisting on this R matrix? Because this R matrix satisfies the so-called Young-Baxter equation, which is the following. And this is also something that you can do even by hand. No, you don't even need Mathematica to do this. I mean, do it by hand, it really means that you are bored sick, okay? If you put it in Mathematica, it's a little bit faster. But yeah, okay, so this is the classical Young-Baxter equation, and the quantum system we get is d psi over dy j, sorry, equal to h j psi, in which this hj is the sum over E different from j of ij uj minus ui. And as I said, this is called the KZ, the Thermological Equation, and I think I stop here. Sorry for going slightly over time.
Okay, thank you very much, Marta, for a wonderful lecture. Let's all give Marta a round of applause. So are there any questions for Marta? If you have a question, feel free to unmute yourself and just ask.
Why does it satisfy the classical Yang-Baxter instead of the quantum Yang-Baxter?
Well, in a sense, you see, this is a classical object that I've introduced still. The kind of computations I've done are linear, right? Perhaps that's the best explanation I can give you. So somehow I'm using the standard Lie algebra structure, which is linear, and the Lie Poisson structure, which is linear. So I expect a linear object. I wouldn't expect quantum. I would expect quantum if we were to do a quadratic Poisson bracket. Right?
May I make some comment?
Sure.
Just to think about the quantum analog, of course, you also can, in this you don't need it, but you also can think about this classical R matrix. It means the solution of this Yang-Baxter equation. You can, from this solution, you can obtain solution of associative Yang-Baxter equation. The same R matrix is a solution of associative. If you split your brackets, I mean, consider these brackets like brackets in the Lie algebra associated with associative algebra, which in this case it is just universal enveloping of SL2. In this associative algebra, this R matrix satisfy so-called associative Yang-Baxter solution, which is half of this. I mean, you can write, instead of Yang-Baxter which you wrote, you can write R1, 2, R2, 3, plus or minus, it depends which half of this bracket you choose. And then you have quadratic relation for this R matrix, which is equal to 0 if this is the solution of this. I mean,
I mean,
this associative Yang-Baxter is associativity condition for a new multiplication in universal enveloping algebra.
Mm-hmm.
So it is a quantum interpretation of the same thing. You didn't say it because we don't need it, but in fact, with SL2 you can associate two quantum algebras: quantization of function algebra and quantization of universal enveloping algebra.
Well, and then you
quantum algebras, they are in some sense dual. This is Semyonov-Tenshansky duality, very clearly and very elementary explained in his paper of 90, I don't remember, 91, 92. It is a kind of dual quantum groups.
Mm-hmm.
So this is a very neat way to get the Knizhnik-Zamolodchikov equation, but then supposedly you can go further. You can try to quantize the Knizhnik-Zamolodchikov equation itself. Is that So what happens to this R matrix in that quantization?
I mean, the literature on quantum Thermological is quite, yeah, I haven't really tried to carry out such a naive procedure. No, honestly. So I must say, by the way, that this trick of quantizing in this way was Ilya that taught to me, because in fact, in the paper of Reshetikhin, it just starts with the equation in this form and goes the other way around. So he shows that taking some clever classical limit, then you get to the classical Hamiltonian system behind the Schlesinger equations. But then Ilya showed to me this one, and I thought this is really clever to understand it with your hands rather than with your brain.
Yeah, so that's Ilya Gayur. That's one of our organizers.
Yeah. So the work we have in progress that I was referring to before was to study the equivalent of these Hamiltonian systems when we allow a more complicated structure of the dependence on time, and then quantize that. And that I hope we will put this paper on arXiv in the next. So we decided to put it by the end of this week. I think that's not going to happen because today is already Wednesday, but maybe by the end of next week, I think it's reasonable, but surely by the end of May, she says. Yeah, I mean, you know this situation, right?
Very well.
We all know the situation in which we think something will be submitted by the end of the week.
Does anyone have any other questions?
Well, if no one has a clever question, I have a silly one. When you showed us the kind of the SL2 example, and you went through this, well, let's do this quantization more formally. You kind of left an exercise to us.
Yes.
And I mean, and I can see how you get the commutation with A and C and B and D, but by that procedure, I mean, how can you possibly get the commutation between A and B that was among the set of rules that you gave earlier?
Yeah, I was hoping nobody would ask this question.
Okay. Fine.
So, yeah.
Well done, Matteo.
Okay, no problem. Since it was...
I'm not going to offer you a beer next time I see you. So,
it might take a while.
I don't remember actually now. If you take that beautiful book, beautiful paper by Fadiev and Takhtajan, it's explained there. I don't remember now.
Okay. Can you give a reference to that paper, please?
Yes. Can I give a reference? No, I took it from this book of Charlie Presley, and they refer to Fadiev and Takhtajan. So I think it's in Charlie Presley book, you know, that black and white book, a black and blue book.
I'm afraid not really.
Called Quantum Groups.
Okay.
So it's on Charlie Presley. I can find the exact page. It's just I left it in my office.
Well, okay, but I mean, is Quantum Groups by Charlie Presley?
Charlie Presley. It's a famous book.
Okay.
Okay, let me find it for you. It's a very nice book.
Oh, Jan has found it already in the chat.
Oh, okay. Brilliant. Just let me see this chat then.
Thank you, Jan.
Okay.
Thanks.
And this doesn't allow us to view the book, but maybe we can see inside and I can tell you which part. So this you should be able to download from somewhere on the internet.
Okay, well, or to find in some library.
But we don't endorse it officially.
We don't endorse
Find
doing
in some
that at all.
library. I will
Okay,
find
so-
in the library. Okay.
In the library, I'm pretty sure that it's quite a well-known book, and you should be able to find
Okay,
it
thanks.
easily.
I mean, it's kind of a curiosity, of course, but it was fun.
Now, for me, that book is nice because it's very hands-on. So you really, do the little examples and you understand what the heck these people are talking about. Okay.
Excellent. So any other questions? I see Volodya Rubtsov. Do you have a question?
Me? No.
Yeah. Oh, no.
No.
Yeah.
Probably just one more remark about the notation. Then to feel better the quantum nature of this H hat, maybe it would be useful to know this nominator by omega ij, where omega is just a operator of flip operator.
See, Volodya is saying this, that this matrix R12 is often denoted in the literature in the case of SL2 by the letter omega, which is the permutation operator.
And this permutation operator definitely satisfies quantum Young-Baxter
As well as, yes, that's true. Yeah, okay.
Interesting.
Mhm.
Okay, so if there are no further questions, then I suggest we give Marta another round of warm applause.